students, welcome to our channel Physics class. And today we will do in this lecture some numerical problems which are related to current electricity. We have done with the theory of current electricity and we are familiar with the formulas, and now we'll try to focus on certain numerical problems that are important for your board exam, as well as they will be equally helpful in your competitive exams. So just try these numericals and practice them and have a command on the subject physics. So let us begin with a few examples. First we'll be doing certain numericals which are related to the physical quantity resistance. So resistance, as we all know, it is represented with the symbol capital R. So R always stands for resistance. So first numerical we are going to attempt is that we are given with a wire. There is a wire, and if it is a wire and it is conducting some current, then obviously it will be having some resistance. So the question goes like this, that we have stretched a wire to increase the length by 1%. There is a wire whose length we have increased by 1%. Then we have to find the percentage change in the resistance. So what is the change in the resistance? And the answer we have to give in percentage change. So to solve this numerical, we have to write down the formula. R is equal to rho L upon A. This is the formula. So I'm writing down the question also. So our question goes like that. So to solve this question, we have to write down a formula that goes like R is equal to rho L upon A. And you have to find a change in R. Then we write it down as change in R with delta R. So just focus on this delta R upon R. It may be written as first point is rho. So that is the ratio of change in the resistivity upon resistivity. Then here we have length. So this is the change in length upon the length. And A is in denominator. So we write down as change in the cross section upon the cross section. So whenever there is a change, you can write down, but this change should be small. Always mind this thing, that whenever the change is small, then we can write down this formula. And also, if there is a change in length, this is equal to minus delta A upon A. This relation we can write down whenever the change is small. So now we have to calculate the percentage change in resistance. So this will be the percentage change in resistance. So directly apply the formula delta R upon R. Now what is the change in resistivity? There is no change in the resistivity because resistivity depends on temperature on the material. So if you want to know what are the properties of resistivity, you can quickly refer to the lecture. I have given the link below. So here, just for now, we can say that the change in resistivity is 0. Plus the change in length, that is a percentage change in length, that is given as 1. So write this down, value is 1. And from this relation, we can say that whenever there is a change in the length, then there is a change in the cross-section area in the negative. That means you are increasing the length. When the cross-section area will have negative effect, it will be decreased. So the change anyways is similar. So it will also be 1%. So change in resistivity is 0, change in length is 1%, and due to the change in length, the change in cross section is also 1%. So the change in resistance we can write down, that is a percentage change in resistance. That's 0 plus 1 plus 1, that gives us 2. So you can simply write down then the change in resistance in percentage is 2%. So 2% is the answer we were looking for. So this numerical is now done. So let's come to the next numerical. We have to calculate the current flowing in this part of the circuit. So here given with this part of the circuit, here we have 2 points, point A and point B. Point A is having the voltage of 10 volts and point B is having the voltage of 4 volts. So these 2 points are at different voltages. That is our first observation. Second observation is that between these 2 points we are having this resistance R, and whose value is given. So what is given to us? It is given to us that the voltage at point A is equal to 10 volt and the voltage at point B is equal to 4 volt. As I always tell you that whenever you are solving any numerical, first of all, write down what is given to you and then what is to be calculated and what is the formula. That is a proper way of solving any numerical and attempting it fast. So V is 10 volt, VB is 4 volt and R is given as 2 ohm. So these are the three things which are given to us. And what is asked? What is asked is what is the value of the current that will be flowing. So simply this is V, R and I. So we can use Ohm's law to solve this numerical. Ohm's law will work well. So what is our Ohm's law? Ohm's law is simply V is equal to IR. If I write down in caps, V is equal to IR, then we have to calculate the value of I. So I will be simply V upon R. So just write in the value. V is the voltage difference, that is VA minus VB. So that comes out to be 6 volts. So write in the value 6 volts. And the value of resistance is given as 2 ohm. So this is 2 ohm. Then our current will be 3 ampere. Right? So simply using Ohm's law, you can solve such simple numericals. And if you see, it might seem difficult to you, but if you apply Ohm's law, then this just you can solve in fraction of seconds. So let's do one more numerical. So in this numerical, we are given with a circuit. The circuit goes like this. We have 4 points A, B, C and D, and here we are having there is a resistance, then there is a cell, then in the below part we are also having one resistance, and there is one more cell. So here we are having opposite side cells and these opposite sides resistance. So that is it, what is given to us. This point is given as point A, then this is B, then this is C, and this is D. These are the 4 points given. And the value of this, the voltage on the cell is 20 volts, on this is 10 volts, this resistance is of 5 ohm, and this resistance is of 2 ohm. That is what is given to us. V is given to us and R is given to us. So we have to find out the current. It is asked to find out the current I. And where we need to find out? In the wire BD. So there is a wire between point B, this is point B and this is point D. So we have to find out the current which is flowing in the wire BD. So just join B to D. Okay, so we have to find current I here. What is the current which is flowing in this wire BD? So now we have to solve this. So for current we need the voltage between these 2 points. So let us say initially we can consider that potential at point D, VD, we can take it as 0. We are taking this reference point, D as a reference point, and say we are saying that the voltage at point D is equal to 0. So if it is 0, you can write down V is equal to 0 here. Then you can write down the potential at other points. So it is 0, then here it is 20 volts. So point C will be at 20 volts. Here voltage is 20 volts plus 20 volts because the cell has given the voltage. And here if we go, so if these two are connected, it is at 0, then B point will be also at 0 potential. And if we come to point A, Then here it is given with 10 volts. So here it will be 10 volts plus 10 volt you can write down. And if you take the direction of flowing of the current, voltage is this here, and here we are having 5 ohm. So here it is 10 volt and it is 2 ohm. So the current that will come out will be I is equal to V upon R. So the current here will be 4 ampere. So the current here will be 5 ampere. 10 upon 2 will give us 5 ampere. And similarly here it is 20 and this is 5. So the current will be 4 ampere here. So now we can write down. If you want to calculate the current in wire AD. So current in wire AD is equal to 5 ampere. Because that is 10 upon 2, so that will give us 5 ampere. And current in wire CB is equal to 4 ampere. Because I is equal to V upon R, so V is 20 and R is 5, so 20 upon 5 will give us 4 ampere. So here the current that is coming is 5 ampere and here it is going is 4 ampere. It is 4 ampere here and in this hand it is 4 ampere, so 5 ampere. If you see here at this point at the junction point, then 5 ampere is going here and here we are getting 4 ampere. So the remaining part will be going to B and D. So the current in wire BD, you can easily write down current in wire BD. So this is 5 here and 4 here. So the remaining current will go to this point, this wire B and D. So we will have 1 ampere of current from D to B. So here it is 5 ampere. Now this is say 1 ampere we have calculated. So remaining 4 ampere will go here. And 4 ampere, 1 ampere is coming from here, so again it will be 5 ampere. So easily we have done with this numerical. So this numerical is now done. We do one more numerical of such type. So here again the circuit that is given to us is like we are having 2 resistances. This is resistance 1. And this resistance 2 in a single arm, and here we are connecting one cell of 10 volts, and in between we have one more resistance, and there's one more cell of 30 volts, and here we have one more cell of 14 volts. So this is 1 ohm, 2 ohm, 2 ohm, and this we can say this is point A, this is point B, this is C, D, E and F. So these are the 6 points A, B, C, D, E, F. These are the 6 points. Now we have to find out the current in each wire. We have to find the current in each wire. So again we can go on this similar lines. We can work like this. We can take any point at potential 0. So we can say for instance we take this point as B has potential 0, so these three are connected. So there is no any voltage source connected between these 3 points. So voltage will be 0 here, and similarly voltage will be 0 here because there is no voltage source between these 3 points. So here we are having this voltage source of 10 volt. So at point F we can write down that the voltage. So at point F voltage here will be 10 volts. But since there is a voltage source connected, so this will be 10 volts. At point D, you can see we go like this. So this will be minus because all these are in plus. We go from minus to plus, minus to plus, and minus to plus. And here you go from plus to minus. You can write it down as minus 14 volts. Or if you are taking these as negative, minus 10 volt, and then you can take it as positive. But since we are in this numerical, if we take this minus to plus as 10 volt, then this will be minus 14 volt. And here this is 30 volt. So again it will be at point here. You can write it down. V is equal to plus 30 volts here. Right? But at E, no potential is known because here it is 10 volts, here it is minus 14 volts, and here is plus 30 volts. So at E, we cannot write down direct away what is the voltage. So we take any value. Let us say that the voltage at point E is having any value X. So now this E point is our main concern where we do not know the voltage. So what we can do here, we can use the Kirchoff's law. So I'm applying the Kirchoff's law. We can use the junction law because here we are having a junction, right? So junction is that the sum of the currents, the total of the current that is entering is equal to the current that is leaving. That means the junction stores no current. So we have to apply this. So here the voltage is X and here the voltage is 10. So we can write down I is equal to V upon R. So the potential difference between these 2 points is X minus 10. And resistance is 1. Just I repeat this once more because Kirchoff's junction law we used, and we have to write on the current that the current entering is equal to current leaving. So if we consider 2 points E and F, so the voltage difference is X minus 10 between point E and F, and the resistance present here is 1 ohm. So we can write down the current as X minus 10 as the voltage divided with the resistance. This is the current plus. Here you see it is X, and at this point it is 30. That is the voltage difference between these 2 points, X minus 30, and the resistance is 2. So you can write it down as X minus 30 upon 2. So this is current, this is current. And if you consider these 2 points between E and D, here the voltage is minus 14, here the voltage is X, and the resistance is 2 ohm. So you write down between E and D. So this is because we are moving in this direction. So this is X minus minus 14. So X minus minus 14 will give us X plus 14. Is it clear? Because it is with the negative sign. Had it been positive, so it would have been X minus 14. But it was already with the negative sign. So X minus minus 14 will give you X plus 14. And the resistance present between them is 2 ohm. So X plus 14 upon 2. So we have written this is I, this is I, and this is I. So these 3 are currents, and this is equal to 0. So the sum of currents entering plus leaving is equal to 0. So if you solve this, X minus 10 plus, so if you solve this, then you have, this is 2X minus 20 plus X minus 30 plus X plus 14 is equal to 0. So if you do the total, that is 2X plus X plus X. So this is total 4X. And this is minus 20, minus 30, so minus 15 and plus 14. So minus 50 plus 14 will give you 36. It's equal to 0, or you get the value of X is equal to 36 upon 4, that is 9. So we get the value of X equals to 9. That means the voltage at point E is 9 volts. So we get the value of X as 9. So we can write it down as 9 volts here. So make this X as 9. Now we can calculate the current. So current in EF is X minus 10 upon 1. So we can write on current in EF, whatever the value of EF we have taken. Now we know the X, so we can calculate the current in each branch. So this is equal to X minus 10 upon 1. So that is 10 minus 9 upon 1. So that is equal to 1 ampere. And the direction is from F to E because we have taken 10 minus 9. So that is why the direction is from F to E. Just if you like to ask that why we have not written 9 minus 10 upon 1, you can also write it down as 9 minus 10 upon 1. So we'll get it minus 1 ampere. But minus 1 ampere means the current will flow from, if you are calculating E to F, 9 minus 10 means E to F. So if you move from E to F, then the current you are getting is negative. That means the current is flowing from F to E. So if you can take it as positive, then it's from F to E. And if you take it as negative, then again it is F to E. So this negative will only give you the direction. So you can do both ways, but always you will get the magnitude as 1 ampere and the direction is from F to E. Now similarly we can calculate the current in wire B. EF where we have calculated. Now BE we want to calculate. So BE is, this is X minus 30 upon 2. Again you can do it. We start from B to E. And this is 30 minus 9 upon 2. And this is 22 upon 2. And this is 21 upon 2. And 21 upon 2 will give you as 10.5. So this is 10.5 ampere from B to E. If you write it down as 9 minus 30 upon 2, again you will get minus 10.5. That means if you move from E to B, you are getting the current as negative. So the current will be from B to E. And similarly in the wire DE, we can calculate the current. So current in D is equal to 9 plus 14 upon 2. So this is 9 plus 14 upon 2. 9 plus 14 will give you 23. 23 upon 2 is equal to 11.5 ampere. And the direction will be from E to D. Right? Because we have taken 9 minus 1 is 14. And if you write down minus 14 minus 14 minus 9, then again you will have this is minus. So you will move from E to D. From E to D. So now we have calculated the current in each wire. So that means we are done with this numerical. So this numerical is now done. So whenever you are having such, if you're finding it complex, always use Kirchoff's law because Kirchoff's law can make it very easy. And you can use the convention you want. Either you will get minus or plus, so that will give you the direction. But always be aware of the formulas you are applying and the law you are using. Just stick to that and you will always get the correct answer. So let's move to the next one. So for the resistance we have done up with numericals. Now we can do few on current. So let us say that we have in a circuit arrangement here, we are having 3 bulbs. We are given with 3 electric bulbs. Bulb 1, this is bulb 2, and this is bulb 3. And these 3 bulbs are connected in series and they are again connected to a voltage source, that is a cell. And this cell voltage is given to you as 200 volts. So this is our bulb 1, bulb 2 and bulb 3. So these 3 are electric bulbs. This is a circuit which is given to you. 3 bulbs are connected in series and then they are connected to a voltage source of 200 volt. And what is given to you? It is given to you that for bulb 1, V is equal to 200 volts and the power P is equal to 50 volt. Similarly for bulb 2, voltage V is equal to 200 volts and power P is equal to 100 volt. For bulb 3, voltage V is equal to 200 volt and power P is equal to 25 watt. So that is what is given to us in the question. Now what we need to find out? We need to find out. So this question has two parts. We have to calculate the current in each bulb, current in 1, current in 2 and current in 3. And the second part is which bulb will give more light. That means which bulb will glow brighter. So if it is glowing brighter, that means it is giving more light. So let us do them one by one. Current in each bulb, we need to calculate the current. So let us go with the solution for this numerical. Right, so what is given to us? Power is given to us and voltage is given to us. Now we know that the power is given with the formula P is equal to V square upon R. Now if you don't remember this, you will simply remember this P is equal to I square R. Then also it is okay. So you can write down V is equal to IR. Then I is equal to V upon R. Then put this value. So P is equal to V square upon R square into R. So this 1 R cancels out. That means P is equal to V square upon R. So any of the formula if you remember for the power, you can solve this. If you direct away remember this formula, this is equally good. So P is equal to V square upon R. So P is given to us, V is given to us, only R is unknown. So write down the value of R as R is equal to V square upon P. That means we can also calculate the resistance for each bulb. So resistance for bulb 1 will be equal to V square upon P. That means 200 square upon 50. So that is resistance for bulb 1. Resistance for bulb 2 will be written as V square upon P. Again V square is 200. So that means 200 square upon 100. And the resistance of bulb 3 is equal to V square upon P. Again the voltage is same, 200 square upon P is 25. Right? So we have written the 3 resistances. Power is given, voltage is given, resistance we have written. Now we have to calculate the current in each bulb. Now we can write down, because we have the voltage, we have the resistance, so we can write down the current. Current in each bulb. 2 things are known to us, third thing we can easily write down. So current in each bulb comes out to be I is equal to V upon R. So what is the voltage? Voltage is 200 volt. See here, this is 200 volt that is given. So each bulb is having the voltage source of 200 volts. So write down 200 here. This 200 is because of the cell which is acting as a voltage source. And this is V upon R. R will be because these 3 are in series. You see these 3 bulbs are in series. So their resistance will add up, because whatever for the series combination, the total resistance R is equal to R1 plus R2 plus R3, because the 3 bulbs are in series. We want to know what we do if these are in series or these are in parallel combination, then you can refer to our lecture. But as for now, because these 3 resistances we have calculated R1, R2, R3, if the bulb are in series, that means these 3 resistances are in series. So the total resistance R will be R1 plus R2 plus R3. The current I is equal to V upon R. Voltage is 200. Current is the sum of these 3. So put the value. So this is 200 upon, put the value R1 plus R2 plus R3. So in these 3 terms, 200 square, 200 square, 200 square. So take 200 square as common just to simplify. 200 square is common. Here it is 1 upon 50. Here it is 1 upon 100. And the third term it is 1 upon 25. Right? So now we can easily simplify doing simple mathematics. So I is equal to 200 divided with 200 square. And if I take 100 as LCM, then it will be 2 plus 1 plus 4. Right? So this is 200. 200 will cancel out. So this is only 1 and this 100 will go upward. So this is 100 upon 200 is remaining, and this is 2 plus 1 plus 4, 5, 6, 7. So 100 cancels, this 200 and remaining is 200, 200 is 2, 7 2 is 40. So this comes out to be 1 upon 14 amperes is the current, right? So the current in each bulb is 1 upon 14 ampere. Simply we have calculated using 2 formula of power and formula of resistance from Ohm's law. So using these two formula, you have calculated this. And so the first part is done now. Second, which bulb will give more light? So let's see. Now if you look at the resistance of these three bulbs, this is 200 square upon 50. So numerator is same in these three. Just have a close look on these three. What is it? 200 square upon 50, 200 square upon 100, 200 square upon 25. So whose resistance is large? This resistance is large because it's upon 25, right? So R3 is having the largest resistance because it's divided with the smallest quantity. 25 is the smallest quantity among 50, 100 and 25. So R3 is greater, then second one is 50. Okay, because 50 is the next quantity, R3 is greater than R1 and then comes R2 because it's divided with 100. So this is the smallest resistance. So this is the order of resistance. Now again we know the power. Power is equal to I square R. So that means the power will be proportional to R because the current we have calculated is same. Current is 1 upon 40 ampere. So the power will only depend on the resistance. So if the resistance is having high value, power will be high. So who is having the largest resistance? Bulb 3 is having the largest resistance. So it will give the largest power or the highest power. Highest resistance, highest power. So power of bulb 3 is greater than power of bulb 1 and it is greater than power of bulb 2. So we can say 3 is glowing brightest, then comes bulb 1 and then comes bulb 2. So bulb 3 will give more light. And if you want the order, we can also give you the order. Then comes bulb 1 and then comes bulb 2. So don't use logic if you are not using the formula correct. Simply use the formula for power and P is equal to I square R. So current is same, so it will depend on the resistance. So the resistance is lowest. If you go to the figure, then you see that is bulb 3 is of 25 watt, bulb 1 is of 50 watt, bulb 2 is of 100 watt. That means individually if you see power, then do not conclude from that bulb of 100 watt will glow brighter because these three are in series. And here's the voltage. Then we have to look at the current because voltage is 200 volt here. That is the voltage source. And the current is same in each of these. So let's go to the formula of power. Power is I square R. So I is same, so it is directly proportional to R. Now you have to look at the resistance. You need not look at the power of individual bulb. Right? So that is how we commit mistakes. We use common logic. We use the power direct away because that is in the back of our mind that which is having a more power will glow brighter. No, but here if you have gone through the theory, then stick to the formula because when you stick to the formula, your answer will never be wrong. So our right answer is that bulb 3 will glow brightest. So you also grow brighter and do the numericals right. Okay, so let's move to the next one. So we do one more numerical on current. So here we are given the three resistances which are connected in series. One end we have point A, other end we have point B. And there's one more resistance which is connected in parallel between these two resistances. Right? Here is also R. So we have to find the current and resistance P. This is our resistance P. If voltage supply between A and B is V volts. So these are the 2 points A and B. Voltage supply, that means we have connected a cell. So what we are given with that the voltage is equal to V volts between A and B. So VAB is equal to V volts. That is what we are given. And what we have to find out, this is given. And what we need to find out, the value of resistance R. What is the value of P? What is P? P is a resistance. So we have to find out the value of this resistance. That is our question. So let us go with the solution. So We need to solve this numerical. How will do? So this is our point A and this is our point B. So the voltage at this point will be equal to the voltage at A, and the voltage at this point will be equal to the voltage at B. And since this is also connected, so here voltage here also will be VB. Right? Voltage here is VB and this point is connected here. So here, because there is no resistance in between or no voltage source in between, so the voltage here will be also VB. And say this point, if we take a C, so we need to modify the circuit. We have to draw it again. If we draw it again, so we have to modify the circuit. So this is how we have modified the circuit. This is point A, this is point B, and here we are having two. Here you can see these are the two resistors in series. So here we have drawn these two resistors which are in series. So it is like this. And this is point P, which is connected with them in parallel. So this is a P we have drawn, and these are the two resistors R and R. Because you can say that this resistance is R, and this resistance is R, and this resistance is also R. Right? That is given to us that these are the three resistances R. So we have drawn this is R, and these are the two resistances which are in. So here you can see that this resistance is in parallel with these two. A and B. So these are the two resistors we have drawn. And this one we have drawn it as here, and this is P. If you can see, P is between point A and C, so between point A and C. So how you do? You do like that between A and B we are having these two resistances like this. So these two resistances I have drawn here, and between A and C there is a resistance. So between A and C there is this resistance P. So between A and C we have drawn this resistance P. So this is the equivalent circuit. Now we can find out the equivalent resistance. So if you go here, then we are having this one. If we calculate the equivalent resistance for this, here these two are in parallel. So if we get this R dash, so 1 upon R dash is equal to 1 upon R plus 1 upon R. So that means 1 upon R dash is equal to 2 upon R, or R dash is equal to R upon 2. So in place of these two, you can write it down as M upon 2. So we can replace this with R upon 2. So here we can replace this with R by 2 because these were two in parallel. So this is R by 2. So now we are having this P, R by 2 and R. Now this P is again given to us as R. So this is R, R and R by 2. So this is R plus R by 2. This total is R plus R by 2. So if you take this part, so here if you calculate the resistance, R double dash can be equal to R plus R by 2. So this is equal to 3R by 2. Right, these two are in series, so this equivalent is equal to 3R by 2, and this is in parallel. So if you calculate 1 upon R equivalent resistance, and this is equal to 1 upon R1 plus 1 upon R2. So this is equal to 2 upon 3R plus 1 upon R. So if you calculate, if you take 3R is common, and this is 2 plus 3, this is equal to 5 upon 3R. That means the equivalent resistance will be equal to 3R upon 5. So that is what is the equivalent resistance. Now if we know the resistance and voltage is given to us as V volts, so we can calculate the current. Equivalent current, so I is equal to V upon R, so it is equal to V upon R. So that will be the current. So that is the current which is flowing. Now we have to calculate for this resistance P. What is asked? That if you are having the resistance P, then what is the current in the resistance P? So we need to write down current P. We have drawn this equivalent circuit, then we have done for the resistors, we got the current, and now we have to calculate the current in this particular resistance P. So this will be equal to V upon R. Now if we look at R, this is R and this is R plus R by 2. So this is R plus R by 2 upon R. So this is equal to R plus R by 2, R by 2. R plus R by 2 will give you 3R by 2. So this is 3R by 2 plus R. So 3R by 2 we can write on now. 3 by 2R. So this will be equivalent resistance R plus 3 by R by 2 and R. So this is the value of V and this is the value of total resistance. So we'll get the current. I is equal to V upon R simply using Ohm's law. So this R cancels out with this. So this is equal to 5V upon 3 and here 1.5 plus 1. So this is 2.5. So this is 2.5 with an arrow. So 3 by 2 plus 1, so this is 5 by 2. 5 by 2. So this 5 cancels out and we are left with 2V upon 3 R. So the current in resistance P is equal to 2V upon 3R. So our answer is that the current in P is equal to 2V upon 3R. That is how this numerical is done. So simply use the connection of resistances, then calculate the equivalent resistance, then you get the voltage, then you get the total current, and then you can shift to the particular current in a resistance P. Next question, we have to find the equivalent resistance between 2 points. So we are given with, you can say that we are having three resistance in series. We have 3 resistance. And here we have point A and this is point B. And between these 2 points A and B, we have 3 resistance in series and 1 resistance is connected between these 2 in parallel, and similarly 1 more resistance is connected between the last 2 and that 2 in parallel. So each resistance is having the value of R. All of these resistance, we have the value of R. Now we have to calculate the equivalent resistance. So this equivalent resistance we have to calculate between A and B, point A and point B. This is the question we have to solve. So now let us go for the solution. So how we can solve this? We are given with the circuit diagram, and as you can see that this R, this R, this R, this R, this R. So as you can see, we have 5 resistances in all, and so these 2, one is connected between these 2 and one is connected between these 2. So that means if we take here, there is a pair for this resistance, we are having a pair of this resistance, and similarly for this resistance, we are having a pair of this resistance. So these are the 2 resistance, and then it is connected in parallel, and these are the 2 resistance which are connected in parallel. So we can draw it somewhat like this. we draw resistance R here, then one more resistance R here. So these are the two resistances R and R. And similarly, if we take a point, any point here, and again we get make a resistance R. And here one more resistance R. It's connected to this point, and between these two resistances we have R, and between these two resistances we have R. That's one resistance, right? So we can write on these pointers, say at this point we say C, and this point we call as D. Then between A and C we have the resistance parallel. So this becomes like A, this is B, this is C, and this is D. So between C and D we have one resistance, and between A and D we are having this and this, and similarly between C and D we are having these two and this, C and D, these two and this. So that is how we can draw an equivalent circuit. So this is A, B, C, D. So that forms a Wheatstone bridge, if you see. So this is a condition of a Wheatstone bridge, right? So this shows a Wheatstone bridge, and we know Wheatstone bridge. If you go to the theory, my lectures, if you go to the Wheatstone bridge, the link for the lecture is mentioned below. You can quickly go through it and find out the theory. So we take it this is R1, R2, R3, and R4. So this is R1, R2, R3, R4, and the balance condition of the bridge is R2 upon R1 is equal to R4 upon R3. So say this is R1, this is R2, this is R3, and this is R4. So R2 upon R1 is equal to R4 upon R3. So that condition is satisfied here because R upon R is equal to R upon R. So the condition of the balancing of the Wheatstone bridge is satisfied. So we can calculate the equivalent resistance. So we can write down the equivalent resistance. R equivalent is equal to 2R plus 2R upon 2R plus 2R. So therefore the value of the equivalent resistance 7 2R plus 2R will be 4R squared, and this is 4R. As a condition, how we can calculate the equivalent resistance, it is satisfying the condition of a balanced Wheatstone bridge. So this 4 and 4 cancels out, and 1R cancels with this R, so we are left with R. The equivalent resistance for this condition, for this modified circuit, so equivalent resistance is R. So we have now done up with. So we are now done up with this numericals. So again we will find out the equivalent resistance. Next question we go to, like, whatever is given to us is something like this. So we are having this. So here we are given with the 8 resistances. 4 are in the form of a Wheatstone bridge, like I am drawing here. And these 4 are in the form of a Wheatstone bridge. And the point that is given in the question is this point we can take as A, and this point we can take as B. And here between this A and B, if you take this at the midpoint, and we have one resistance and one resistance. And between these two opposite points, the resistance R and the resistance R. So all these resistances are R. So each of these resistances is having the value of R. Now we have to solve this. So in order to find the solution, we have to modify the circuit first. So write down the solution for this. We can write it down as whatever is given is the circuit only, and then we have to find out the equivalent resistance. R equivalent is to be calculated using the circuit diagram. And this midpoint we can call as, this is A and B, so we can name them C and D, and this midpoint we can call as E. So now we have 5 points as A, B, C, D and E. So now we want to redraw the circuit because this is no more Wheatstone bridge. We are having This is 4 plus 4, so we are having 4 plus 4, that is 8 resistance in all, so there is nowhere we can modify this up to Wheatstone bridge. So what we do is we try to draw an equivalent circuit of this, and if we are done with the equivalent circuit, then we can easily calculate the equivalent resistance. So the modified circuit we want to draw is that we take any point A and this is any point B. So just try to make it easy. So between A and B we are having two resistances and E is the midpoint. So let us say that E is the midpoint, and here we are having one resistance R and here one more resistance R. So this is R and this is R, so we are done up with this. And the C point, if we shift downward, if we take the C point downward, okay, so that C and D points coincide. So we are getting the thing that between C and D we are having these two resistances, and between this D also we are having three resistances. So we want to take this point C down to D so that these 2 points coincide. So this is a common point we can take, that C and D now coincides. So between A and C, if you see, there is a resistance R that I am drawing as. So this is the resistance R, this point C and D, and if I draw this resistance, then this is also a R, right? And there is one more resistance R, which we can draw as that this R is between E and C. So this is E and C. So this one is between point E and point C. So this is one more resistance, say this is R, right? So for C I've drawn this, and this. Now come to point D. D, between A and D we have resistance R, so here you can take any resistance R, any resistance R, draw. And here this is any resistance R between D and D. So say this is resistance R I'm drawing. And there's one more resistance R here. So this I can draw as. See, simply we have done nothing. We have shifted this point C to D. So these are like we have whatever is in the diagram between A and C, between B and C, between C and E, between D and A, D and B and D and E. So these resistances we have drawn like this. So this is called as a folding of the circuit. If you are having a page and you just fold it down into half, then we have just folded the circuit to make it much easier. So now we see this is R, and these two are in parallel. So these two resistances R and R in parallel. So the equivalent resistance will be 1 upon R. So the equivalent resistance will be 1 upon R plus 1 upon R. So this is equal to 2 upon R. So that means the equivalent resistance will be equal to R by 2. So for these two it will be R by 2. Similarly for these two it will be R by 2 because these are two are parallel. And for these two also this will be R by 2. So these two are in parallel, these two are in parallel, and these two are in parallel. So now we can make it much easier. This is a point A. This is point E. And this is point B. And here somewhere we have a point C and D. So between A and C or D we have R by 2. This is R by 2. And here also we have a R by 2 between C or D and D. So here also it is R by 2. And between E and C or D, these two are in parallel. So this is again R by 2. These are R and R. These are R by 2 and R by 2. Right? So now if we see that if this satisfies the condition of a Wheatstone bridge, that means R2 upon R1 is equal to R4 upon R3. Let's see. So R2 upon R1 is it equal to R4 upon R3? Yes. So that satisfies the condition. What is the formula? R2 upon R1 is equal to R4 upon R3. What we take in Wheatstone bridge is this is our This is our R1, this is R2, this is R3, and this is R4. So that satisfies the connection. So condition of balanced Wheatstone bridge is satisfied. So if this condition is satisfied, then just like the previous numerical, we can write down the equivalent resistance. So what is the equivalent resistance? Here R and here is R by 2. So this is equal to 2R. R plus R 2R, and this is R by 2 plus R by 2 is R. So 2R multiply R upon 2R plus R. Right? So this is 2R squared upon 3R. So 1R cancels out with this. So this is 2 by 3 of R. That was the equivalent resistance. What we have done, we are given with a diagram. So circuit diagram, and it is nowhere satisfying, it is nowhere equivalent to any Wheatstone bridge. So to make it simple, we have just the folding of the circuit. This is the diagram for the folding circuit. Now we are having 3 pair of R resistance which are in parallel. So we have just calculated the equivalent resistance R by 2, R by 2, R by 2, and here it satisfies the condition of a parallel Wheatstone bridge. And we use the formula for resistance, and we get the final answer is 2 by 3 of R. So that is where by applying these two techniques, our numerical is done. Now we can do certain numericals on cells, because we have done the reflux cells when cells are connected in series, when cells are connected in parallel. So we'll do certain numericals. So let us say we take this circuit, where we are given with this is a cell, and then we have a resistance. Okay, this cell we have a resistance. And our circuit goes like this. So this is what diagram is given to you as, and we have to find out the EMF and internal resistance of a single battery, which is equivalent to the combination of these 3 batteries. So here we are having 3 batteries, battery 1, battery 2, and battery 3, and these will be the internal resistance of the cell, because it is asked in the question that what will be the equivalent EMF and internal resistance of a battery, because if we combine these 3 cells, whatever we will be getting is a battery. So it is asked that what will be the EMF and what will be the internal resistance of the battery, which is equal to the equivalent of the circuit. That means we have to make one cell out of these 3 cells. So we can call this as cell 1, this we can call as cell 2, and this will be called as cell 3. So here we are having 3 cells which are connected like this. So we have to find out the equivalent EMF and resistance. So let us go to the solution. So we have battery 2 and 3 which are connected in a parallel combination. These are opposite in polarity. So these are opposite in polarity. Then we can write down EMF between 2 and 3 cell. This is equal to 10.2 plus, since the opposite in polarity, so this is minus 4/2. This is V upon R we are doing. So between 2 and 3, that will be given as 10/2, that is V upon R, plus, since the polarity is opposite, so this is minus 4/2. So this is I upon R, because these are in parallel, so this is 1/2 plus 1/2. So that comes out to be, this is 10 minus 4, 6/2, and this is half plus half, that is 1. So that will give us 3 volts. So equivalent EMF here will be between 2 and 3 is 3 volts. Resistance, if you see between 2 and 3, it's 1 half and half, so it comes out to be 1. So now we can replace this whole, because for this parallel combination we have calculated. So we have calculated the equivalent EMF and the equivalent internal resistance. So we can replace this whole thing with this. So now we can modify the circuit that we're having a cell of 6 voltage, and resistance here, that means internal resistance is 1 ohm. And then in series you have one more cell which is having the opposite polarity, that is 3 volts. and then the resistance is equal to 1 ohm. So now we are having two cells in series. So you can find out. So this one was cell 1 and this was 2 and 3 when combined they give out this. So you can write down the equivalent EMF for 1, 2 and 3. This is equal to 6 minus 3 because these are connected in opposite polarity. So this is equal to 3 volts. And if you see the resistance 1, 2, 3, then this is equal to 1 ohm plus 1 ohm. So that gives us 2 ohm because these two are in series. Now why we have taken this polarity here? Just look at this. This cell is of 10 volt and this cell is of 4 volt. So whatever is dominating is 10 volt, right? Whatever we are getting here is 3 volts that corresponding to the positive one, and this one we are getting from the positive one. So this will be in our resultant circuit. So if it is connected to the negative, it will be connected to the negative. Had this cell been just opposite of this, then we have drawn it like this. Right? So that is the point you have to remember for this numerical, and whenever you are given the cell in combination, then you have to make a circuit simple. Here we have made it simple by calculating these two in parallel, and then we replace these two cells, and finally for these three cells we calculated equivalent EMF and equivalent resistance. So if you have to use a single battery, then you have to use a battery of 3 volts and resistance of 2 ohm. So now we are done up with this numerical. So now what we are doing is just an application of the potentiometer we have done. As theory we have done up with the potentiometer. So this numerical is based on potentiometer. You want to go into the detail of the potentiometer, then you can refer to my lecture. The link is given below and you can easily read the theory. And here we are using the first application of the potentiometer, where we use the potentiometer to determine the EMF of an unknown cell, and it is compared with a standard cell. So in potentiometer we are having two cells. This is a standard cell and this is an unknown cell. This is our standard cell. And this is an unknown cell. So for the standard cell, EMF is given to us as 1.2 volts. And for this, the balance point is observed as L1 is equal to 56 centimeter. And for the unknown cell with the EMF, which is maybe taken as E2, and the balance length is observed at 80 centimeter. And this one is unknown to us. That's what we have to determine. That is the question. So we have to determine the EMF of the unknown cell. So now let us quickly move to the solution. So let us now quickly move to the solution. If you know the theory, then it is just a fraction of seconds to solve this numerical. What is given to us? These all things are given to us. So that is what is given, and that is what is unknown we need to find out. So using the potentiometer application, when we put the standard cell, then we get this balance length as L1. So this E1 is equal to X L1. And when we use this unknown cell, then E2 is equal to X L2. This is a formula that comes from the potentiometer. So if you take the ratio of these two, then E1 upon E2 is simply X cancels out. This is L1 upon L2. So if you need to find out E2, then this will be simply E1 and multiplied with L2 upon L1. So E1 value is known to us, 1.2 volts, then L2 is 80 and L1 is 56 centimeter. So if you calculate, this comes out to be. So if you put all these values, the answer comes out to be as 1.6 volt. So that is the answer for EMF of the unknown cell. So see how easy it gets if you remember the formula, and formula you remember if you are thoroughly gone with the theory. So it's done. We would like to do one more numerical on the potentiometer experiment. So in this question, what is given to you? Here you have to find the internal resistance R of a cell. What is the value for R? That is to be known. And it is given to us that when we use any cell, then the balance length comes out at L1. So for E dash, the balance length is L dash. And when we use any cell and an internal resistance, then you get IR, then you get the balance length as L2. So in the first arrangement, we are using any cell whose EMF is E dash and the balance length is L dash. But in the second arrangement, you are using the cell as well as a external resistance R, and the balance that comes out to be is. So we can take it, say L1 non dash, you can take it as L1 and L2. So now the balance length is L2. So from the first arrangement, if the cell is used as the balance length is L1, so we can write down that this E dash is equal to XL1 because the balance length is L1 and cell. And second one, we are using LAM, we are using cell as well as external resistance. So this IR is equal to XL2. Now using this, we are using a cell, so we can calculate this current very easily. This is the EMF of the cell plus the internal resistance and external resistance. So just put the value I here, so we get E dash upon R dash plus R is equal to XL2. So put the value 5, this is the value 5. So XL2 and upon R will come from this side, so XL2 upon R. And from here, we got it. The value of E dash is equal to XL1. So again implies E dash is equal to XL1. XL1 upon R dash plus R is equal to XL2 upon R. So from this equation, we can simply write it down here as this E dash is equal to XL1. So XL1 upon R dash plus R, this is equal to XL2 upon R. So X cancels out from here. So what we got is L1 upon R dash plus R is equal to L2 upon R. So just simplify this, L1R is equal to R dash L2 plus R L2. So from here we get the value of R dash is equal to L1 minus L2 upon L2 into R. So that is a internal resistance of the cell. So this numerical is now done. So that's all for today. If you want to go through the theory or learn more such numericals, then like and share and subscribe to our channel Physics Class so that you receive notifications for more such lectures. Thank you.